You know how the Earth goes around the Sun, right? Well, the Sun and all the planets, including Earth, are actually moving around something even bigger, the center of the Milky Way galaxy. It's like a huge spinning top, and we're all stuck to it, moving around and around. Imagine you're on a giant merry-go-round, and it's taking a really, really long time to go around. That's what's happening with our solar system. It takes about 240 million years to complete one full trip around the Milky Way. That's way longer than humans have even existed. As we move around the galaxy, we're also moving up and down, like a wave in the ocean. It's a pretty cool ride, and it means we get to see different parts of the galaxy and experience different things. Like, sometimes we pass through areas with lots of stars and gas, and sometimes we're in a quieter part of the galaxy. The Milky Way is like a big spiral staircase, with stars and planets all stuck to the steps. We're on one of the arms of the spiral, called the Orion Arm. And at the very center of the Milky Way, there's a huge black hole. It's like a super powerful vacuum cleaner that keeps everything in the galaxy stuck to it. As we move through the galaxy, we're also bumping into other stars and galaxies, and that can affect us. Like, it can change the way the Earth gets heated by the sun, or even affect the weather. It's like being on a big cosmic adventure. And get this, the Milky Way itself is moving, too. It's like it's dancing with other galaxies, and sometimes they even crash into each other. It's a pretty wild ride, and we're just along for the journey. So, what's next? Well, we'll just keep on moving, keep on orbiting, and see where the universe takes us. It's going to be a wild ride, and we're lucky to be a part of it. There's a huge black hole at the center of our galaxy, and it's not sleeping. It's actually really active, making super bright X-ray flashes almost every day. These flashes are like super powerful light bulbs turning on and off, making the black hole shine 10 to 100 times brighter than usual. Scientists have been watching this black hole for 15 years using a special space telescope called the Swift Observatory. They found out that the black hole has periods where it's more active, and periods where it's quieter. It's like it's breathing, sometimes it's fast, sometimes it's slow. The weird thing is, nobody knows why it's doing this. Scientists are trying to figure it out, but it's like solving a big puzzle. They don't see any stars or gas clouds causing it, and their best guesses about magnetic fields aren't confirmed yet. It's like the black hole is keeping a secret, and scientists are super curious to find out what's going on. At the heart of the Milky Way, an invisible shield seems to be holding back a cosmic storm. The Milky Way is filled with a vast sea of high-energy cosmic rays, launched by exploding stars and other extreme objects, yet the innermost region of our galaxy is strangely deprived of them. When Xiaoyuan Huang and colleagues mapped this radiation, they found that the Central Molecular Zone, CMZ, near the galactic center has a much lower cosmic ray density than the rest of the galaxy. This points to the presence of a barrier that stops many of these particles from reaching the core. To uncover this, the team analyzed gamma-ray data from NASA's Fermi Gamma-Ray Space Telescope, which tracks the high-energy photons produced when cosmic rays collide with interstellar gas. Outside the very center, the density profile looked roughly constant, as expected from a well-mixed cosmic ray sea. But in the CMZ, just a few hundred light-years across around Sagittarius A*, the inferred density dropped sharply. Because most cosmic rays are charged, the leading suspects are powerful magnetic fields and magneteast winds in the galactic center region. Stronger magnetic fields in the CMZ could deflect incoming particles, while winds driven by activity around the supermassive black hole Sagittarius A* may help sweep lower-energy cosmic rays away. Similar physics already operates on smaller scales in our own solar system, where the solar wind and the heliospheric magnetic field keep many interstellar cosmic rays at bay. If such barriers also exist on larger, galactic scales, they could shape how cosmic rays move between galaxies and influence how we interpret high-energy particles arriving at Earth. Future gamma-ray observatories and radio surveys of the inner Milky Way will be crucial for testing how this hidden shield is built and how it evolves over cosmic time.
The Big Bang Theory is the leading explanation for the origin and evolution of our universe, proposing that the universe began as an infinitely hot, dense point and expanded rapidly around 13.8 billion years ago. This theory is supported by a wealth of observational evidence from many fields of science, including cosmology, astronomy, and particle physics. The term Big Bang was coined by British astronomer Fred Hoyle in 1949, though he was actually a proponent of the rival steady-state theory. The concept of the Big Bang has its roots in the early 20th century. In 1912, American astronomer Vesto Slipher observed that most galaxies are moving away from us, suggesting the universe is expanding. This was further supported by Edwin Hubble in 1929, who formulated Hubble's law: the farther a galaxy is from us, the faster it is receding. This implied the universe is expanding uniformly. Georges Lemaitre, a Belgian priest and physicist, proposed in 1931 that the universe began from a primeval atom, an early version of the Big Bang model. Several key observations support the Big Bang theory: the cosmic microwave background radiation (CMB), the abundance of light elements, galaxy distribution and redshift, and primordial nucleosynthesis. In 1965, Arno Penzias and Robert Wilson discovered a faint glow of microwave radiation filling the universe, a remnant of the intense heat from the early universe. This CMB is a critical piece of evidence, as it matches the predictions of a hot, early universe. According to the Big Bang nucleosynthesis theory, the early universe was hot enough to fuse protons and neutrons into light elements like hydrogen, helium, and lithium. The predicted ratios of these elements match observations. Galaxies and galaxy clusters are distributed uniformly on large scales, and their light is redshifted, indicating the universe is expanding.